Good morning, guys. Hope you're doing well. We're going to talk about our last topic for 110. This is going to be acid-base definitions. Again, I will show you my scratch paper because I can do that on this machine, but I will also upload that to the site so that you can see exactly what it is that I've written. This material is mostly theoretical. We're not going to do a ton of calculations with this, but I will show you the types of calculations that we'll do, and we'll talk about some general question types that you will see on the exam related to this. Well, I'm going to go ahead and share my screen. Minimize a couple of things. I apologize for this. If I can get that thing to move. Sorry. So again, acids and bases, that's what we're talking about. And like I said, the majority of this is going to be definitions. We're going to review what acid-base reactions look like. That's from chapter 4, section 3, and then the section, chapter 15, section 1. So we'll talk about the properties of acids and bases. We'll talk about Bronsted acids and bases, neutralization, and formation of gases. We'll talk about conjugate acids and bases, which we haven't talked about before. The acid-base properties of water, because, water is always weird, so we've got to talk about it separate than everything else. And then we'll talk about equilibrium and equilibrium expressions. We'll talk about pH, how that's measured, what that means, what we can do with all of those calculations. A similar measure, pOH. We'll talk about the fun box, as we call it, which will allow you to do a lot of the calculations, and that is present on the test. We'll talk about the strengths of acids and bases, and acid-base properties of salts, okay? So those are our topics that we're going to be talking about. It looks like a lot of stuff, but it's not going to take as long as it probably looks. So questions, comments, problems? If you have them, you know how to reach me. Reach out via email, send me, give me a call, come to my office. We can talk about anything. Not a problem. So acid-base reactions, let's go through a review. So from chapter 4, we know that acids have a sour taste, they change the colors of plant dyes, they react with some metals to make hydrogen gas, we can see gas formation reactions, and we'll talk about that in a few minutes. They react with carbonates and bicarbonates to make carbon dioxide, and they conduct electricity. Bases have a bitter taste, they feel slippery like soap. Soap is actually made with a base in it. They change colors of plant dyes, and their aqueous-based solutions conduct electricity as well. So both are things that can conduct electricity, and that's because they're electrolytic solutions. We'll talk about that. Now we've talked about the arsenous acid definition, although we didn't necessarily call it that at the time. When we initially talked about acids, we talked about acids being proton donors and bases being OH minus donors. Now that's not really the the entire story there. So acids can be proton donors. There are other ways that we can define them. But bases can also be proton acceptors. The big case that we look at that for is NH3, which is a base. Ammonia is a weak base. NH3 does not generate OH minus itself. It doesn't donate OH minus itself, but it can pick up a proton from water and therefore leaves the OH minus. We'll walk through that reaction in a few minutes. And therefore it does qualify as a base. It raises the pH. So those are things that we can talk about. A couple of other things. Neutralization reactions. So neutralization reactions happen when an acid and a base come together in solution. What occurs when that happens is that we make a salt, so an anion and a cation, and water. Those are the two products of that. The reaction is complete when we have the same number of moles of acid as we do of base. Now remember, sometimes an acid can be doubly or triply acidic. We'll talk about that later. And so we have to have the right number of moles for that, but we'll get to that in a little bit. And we talked about that in the reaction stoichiometry. We can form gases. We talked about this a little bit. Carbonates and bicarbonates sulfites and sulfides react with acids to form salts that decompose to produce gases. So Na2CO3 plus 2HCl gives me 2 NaCl plus H2CO3, but the H2CO3 spontaneously reacts to give me H2O and CO2. So I can get formation of gases when I do these neutralization reactions. Okay. One of the things that you may have seen in the past is when you add an acid to a base, you get a lot of foaming, and that's because of the formation of the gas that then moves all of the liquid around. Okay. Conjugate acids and bases. So Bronsted acids and bases, so proton donor and or proton acceptor, have what we call conjugate acids and bases. So the acid donates the H plus to the base, which accepts the H plus. And then the remaining part of the acid is called the conjugate base. So let's talk in specific terms about HCl, right? HCl is a strong acid. It has that H plus that it gives up, which can then be picked up by something else, and then leaves us with that Cl minus. That Cl minus is called the conjugate base. Okay, so for every acid we have a conjugate base. For every base we have a conjugate acid. So once it's gone through its typical reaction, it will have a conjugate on the other side. So the acid, once it gives up the proton, has that anion that's left. Right. One of the ways that you'll see this is we occasionally just talk about acids as HA, which is an H for the proton, and then an anion that's on it. And so we talk about those acid base properties there because it doesn't matter what that anion is for a lot of these things that we talk about. So that's one of the things that you may see. Okay. But that anion is a conjugate base. All right. When we talk about ammonia as a weak base, once we add a proton to it, once it accepts a proton from an acid, then it's a conjugate acid itself. It can and does donate that proton to other things from time to time. Okay. And we'll talk about how we decide if that's going to happen or not. One of the things that you need to be able to do is if I give you an acid, you need to be able to identify what is the conjugate base. So if I tell you this is HCl, what's its conjugate base? And that'll be Cl minus. So we remove one H plus from it, and that's the conjugate base. All right. We may ask you in a reaction similar to what you're looking at here, what is the acid and base pair? So in this case, we're looking at the base NH3 accepting a proton to become NH4, which is the conjugate acid. And then H2O acting as an acid to donate a proton to the NH3, which then leaves us with the conjugate base, which is OH minus. The difference between each of those is just H plus. So that's what you're looking at there. Okay. So you need to be able to identify, once I've taken that proton off of the acid, what's its conjugate base and what is the conjugate acid-base pair in a reaction. Okay. So I'm always going to start with a base, go to a conjugate acid. I'm going to start with an acid and go to a conjugate base. Okay. Those are the patterns that we need to be able to identify. Questions, comments, problems? Hopefully not, but if you have them, let me know. Now, water's weird. Water is one of my favorite things because it's so different than most of everything else that we talk about. Now, as I showed you on the last slide, water can act as both an acid, a proton donor, and a base, a proton acceptor. So H2O, the blue one, can react with H2O, the red one. The H2O that's the blue one donates a proton to the H2O, the red one that's the base. So the acid blue H2O donates a proton to the red base H2O. We then get the leftovers of the acid, so the OH minus, and then the addition to the H2O gives us H3O plus. So H2O and H3O plus are a conjugate acid-base pair because the acid has come from the other H2O. I picked it up, and so the H2O red is acting as a base. It then has a conjugate acid on the other side where it's picked up that proton. The H2O blue is acting as a base, or as an acid, sorry, I apologize, as an acid, And therefore, on the other side, it has a conjugate base, which differs only by that one H plus. Now, this is called the autoionization of water. Because it happens between two water molecules, it's autoionization. Now, remember that H3O plus is called the hydronium ion, right? Hydronium is always what exists. H3O plus is always what we have in solution. Except we often don't talk about the H2O part of that. Since it's a pure liquid, we often don't think about it. And so you'll see this as H plus and H3O plus, and they are completely interchangeable. All right. They are technically always exactly the same thing. They are always H3O plus, but we don't always write them as H3O plus. Okay. H plus is actually H3O plus anytime you see it. Okay. You'll see both of those things. It depends on what I'm talking about, which one I'm going to write down. That is a convention that a lot of chemists have. So that's what you're talking about there. Okay. Equilibrium. Let's talk about this concept of equilibrium. So if I consider the reaction of A number of A's reacting with B number of B's going to C number of C's plus D number of D's, where A is an aqueous component, B is a liquid, C is a solid, and D is aqueous. A, B, C, and D are the chemical species. The small a, small b, small c, small d are the stoichiometric coefficients in the balanced equation. AQ stands for aqueous, L is for liquid, S is for solid, and G, which is not shown in this example, is a gas. So these are the physical states. So we have our stoichiometric coefficient, the chemical species, and then the physical state. Now, we haven't talked a lot about physical states. We haven't included them on most of the balanced equations that we do because what we've been talking about so far didn't require it. So we didn't include it. But now you're going to need to include it. And the reason that we need to include it is once we start talking about some of the new topics that we're coming into, and that means this one acid-base topic for the end of 110 and anything you do in 111, you'll need to be worried about what physical state that it's in. We have this thing called equilibrium. And at equilibrium, the reaction in the forward direction, so A plus B going to C plus D is the forward reaction. The reaction in the forward direction it happens at the same time as the reaction in the reverse direction. So I can add C plus D to give me A plus B. Okay, so it can go forward and backward. All right. At equilibrium, both of those are occurring, but not in a rate that I can measure. So it looks to me as an outside observer as if the concentration never changes. Even though we're constantly moving back and forth, we cannot measure that difference. Okay, that's what we call equilibrium. Now, equilibrium is not, 50% or 50% reactant, 50% product. That all depends on what the equilibrium constant is for that reaction. And that's what we're trying to talk about is what does that equilibrium constant look like? So let's talk about that. So an equilibrium constant, an equilibrium expression, the expression of what equilibrium looks like is called KEQ. And it's equal to the concentration of those species raised to their stoichiometric coefficients. The only things that we need to notice about this is that I only have A and D. Why are A and D the only things that are in here? Well, let's go back and look at that equation again. So A is aqueous, B is liquid, C is solid, D is aqueous. Okay, both my aqueous components made it. Awesome. Sweet. Liquids and solids don't. So when we write our K expressions, anything that's in the liquid phase or in the solid phase is not going to appear. The reason for that is because their concentrations are so much higher than than what we have in the aqueous phase that it appears to not be part of that expression. Okay, it's what we call a pseudo not present component. All right. And so the concentrations raised to the power of the coefficient found in the balanced equation. This expression is the same as the concentration of the products over the concentration of the reactants to their stoichiometric coefficients. Okay. No solids or liquids appear in this expression. And bear with me just a moment because I need to fix that. it should be no solids or liquids. The gases do appear, we just haven't included them at this point. So let me back out of this because I need to. I apologize. So no solids or liquids are going to appear. That's because they have very large concentrations comparative to what the aqueous concentrations, and they're effectively part of the constant itself. Now, gases are going to appear for a similar reason. The concentration of materials in the gas phase is very low compared to the volume that it occupies for the most part. So that is going to appear. The other thing is that changes in pressure will lead to changes in concentration and differences in those K expressions for the gases. So that's why we have to include them as well. All right. So this value is a constant at a given temperature. Okay. Temperature affects what that value is, and so that will change things. Now, we can have other things that can affect where we're sitting in that equilibrium, but the equilibrium constant is not going to change. All right. So let's talk about what does all that mean. Why did I bring all of this up? Well, I brought it all up so that we could talk about Kw, which is the equilibrium expression for water. Okay, so Keq for water, or Kw, equals the concentration of the H3O plus times the concentration of the OH minus. This expression is given the special notation Kw because it's for the ionization of water. So like I said, it's Kw in pure water at room temperature. H3O plus and OH minus are both found to be 1.0 times 10 to the minus 7th. That means that Kw has the value of 1.0 times 10 to the minus 14th. A couple of notations for you. Pure water, that's important, and room temperature. So if I change the temperature, the value of that constant changes. All right? And it's really useful to know because we can define acids, bases, and neutral compounds based on their H3O plus concentrations. So if H3O plus equals OH minus, that solution is neutral. So I have the same amount of acid as I do base. If H3O plus is less than OH minus, the solution is basic. Okay, so if I have less acid than I do base, it's a basic solution. If H3O plus is higher than OH minus, the solution is acidic. And if you change one of those concentrations, like if H3O plus goes up, then the OH minus has to go down. That's how that works. Okay. This leads to some other interesting things that we can talk about. So if I know H3O plus, I can use Kw to find OH minus, right? I can take the Kw, divide it by the H3O plus, and that gives me the OH minus. Okay, so I can do that at any time. I know what this value for the Keq for water is. I know what the concentration of one of these is, so I can find the other concentration. A couple of other things that we can do using that. We can define something called pH. You've probably heard of pH in the past. Well, P, that little p, simply means we take the negative log of whatever we're talking about. In this case, we're talking about the H3O plus concentration. So it's listed as pH because we're talking about the H plus. Again, it's that laziness that we're looking at. So it's a logarithmic description, so it's a lot easier for us to work with because there's not so many orders of magnitude that we have to talk about. Since the concentration of hydroxide and hydronium ions are very small, we use another scale to look at them, and a logarithmic scale works for that. So we take the negative log of H3O plus, because if I take the negative log, then that gives me a positive value that I can look at, and that's easy for us to do. It's also dimensionless. This has absolutely no dimension on it because of the math that we've done to it. So if the H3O plus is greater than the OH minus, so the H plus is greater than the OH minus, that means I'm in an acidic solution. And that's greater than 1 times 10 to the minus 7th, right? Because that's what it would be if they were equal to each other. Then the pH is less than 7. So one thing you have to note, if H3O plus is high, pH is lower than 7. It's an inverse relationship, okay? If the H3O plus is less than the OH minus, the H3O plus is less than 1 times 10 to the minus 7th, we know that's a basic solution because the OH minus is greater than the H3O plus, and our pH is above 7. pH decreases as H3O plus increases. So we can calculate pH by taking the negative log of the H3O plus, and I can calculate the H3O plus from the pH if I take 10 to the negative pH. That's the inverse of the negative log. Okay, so that's what we're talking about with those two. Awesome possum. One other concept that we want to introduce to you guys at this point is something called pOH. So just in the same way that we've talked about the H3O plus concentration, we can talk about taking the negative log of the OH minus concentration, and that gives me pOH. So it's a logarithmic description of the hydroxide ion concentration. Since the concentrations of those two things are very small, we use another scale to look at them, and that's why it's logarithmic, and the logarithmic scale works well for that. I take the negative log of the OH minus. This results in a positive number that we can reference, and it's dimensionless, just like before. Now that I know what pH is, negative log of the H3O plus, and I know what pOH is, the negative log of the OH minus, and those two multiplied together, the H3O plus times the OH minus equals Kw, then I can take the negative log of the Kw and get a value for that too. We get 14 if we do that at room temperature, all right? So that means that the negative log of the OH minus plus the negative log of the H3O plus is equal to the negative log of Kw, which means pOH plus pH equals 14. So that's where that expression comes from. And if you want the details about how that's derived, that's what your textbook is for. Okay, it is in your textbook in chapter 15. The H0 plus is greater than the OH minus. We know we're in an acidic situation. OH minus is therefore less than 1 times 10 to the minus 7th. The pOH is greater than 7. Okay, because now we're looking at it from the OH minus scale, so it's greater than 7. Okay, when we're in an acidic solution, right? H3O plus is less than OH minus. Okay, I think I misspoke. Sorry, bear with me just a moment. So H0 plus is greater than OH minus. That we know is an acidic solution, right? That means our OH minus is less than 1 times 10 to the minus 7th, and our pOH therefore has to be greater than 7. Okay, is that right? I hate it when I confuse myself. It's ridiculous.